I'll use the example of a beam, but you can idealize most of the machine elements with some sort of a beam. Right, so anything, any shaft or anything would be supported in some way or other. And then we try to idealize those supports as either pin joints or hinge joints or roller joints. So what I show here is very generic, even though it looks more like civil and not mechanical, but it's kind of universal. So let's say that this is something like this is subject to a load P. And specifically what we are interested in is figuring out the stress at some location. So let's say that when you observe this particular beam, you found that there's a particular point which is weak, right? Some deformity or something you saw, and that point is, let's say, over here. So then what we need to do is blow this up. And then we would like to find the stresses on that. And that is something which will come following this part. That is, given a beam, given loading on it, how do you find the stresses at some point in the beam? So let's say the stresses are sigma y, sigma x, sigma. So this will be sigma y, y. So it turns out that once you know the shear force and bending moment diagram, there's a way to compute the stresses. Okay, so that's the part which I will talk about after I tell you about Mohr Circle. So what Mohr Circle basically helps you to do is it helps you to find the stresses at some angle, which is not necessarily the x and y axis in this case. So if you want to find the stress, say at this orientation or this cut, because you suspect that at that particular surface, you will see that you expect this thing will fail. So you want to find the stresses on that particular inclined surface. So let's say that the stress on this surface is sigma for the normal stress. It's normal because it's normal to that plane. And then there will be a shear stress. So what Mohr Circle does is it tells us a method to compute sigma and tau from sigma x, sigma y, tau xy. It tells us how to find sigma and tau. Okay. Now there's something about this and computers. That is, there were no computers then, or they were very slow. And then they wanted a method which was easy to use in the field. And Mohr Circle is a very easy to use graphical method to solve the problem. Now it turns out that you don't really need Mohr Circle to find sigma and tau. There's actually a formula relating sigma tau and sigma x, tau xy, sigma y. And so by all means, you can skip Mohr Circle and just do it using a computer. That is, there's a plug-in formula. Okay, so what we'll do is I'll show you both things. I think when you solve this problem in the exams, it'd be beneficial that you use Mohr Circle because it's very intuitive, but you're free to use the formula. You'll get the same answer. In fact, you can do it both ways and check your answers. Okay, so the piece which I forgot to tell you is this. You need to know this angle too. So you need to specify theta also, because unless you have theta, you will not know sigma and tau. Okay, so let's see. I can derive the expression for sigma and tau, but I think that's the class time is not a good use of that. What I'll do is I'll post my notes on how to compute sigma and tau by drawing. Essentially, what you do is you draw a free body diagram of that inclined surface, and then you basically use trigonometry to find sigma x in the direction of, you find sigma x, tau x, y, sigma y in the direction of sigma, and then you also resolve it in the direction of tau. When you equate the things, you'll get sigma, there'll be a formula, and tau, there'll be a formula. So I will not do that derivation in class. It will be in your textbook from previous classes. You can refer to that, but I'll post my notes on how I did it. So sometimes, it's good to know the derivations, because given a scenario where you're unsure if this method works, then you can go and look at the derivation. So I will post the derivation later. Sigma as a function of tau x, y, sigma x, sigma y, and theta. So given all these numbers, you can find sigma, and then you can also do that same thing with so you can get this formula. So let me write down the equation for sigma and tau. That is, I'm going to write F1 and F2 and post the derivation later. Okay, so here is a formula for sigma. Yeah, so don't worry about the length of the formula. You'll have all the formulas given to you for the exam. Okay, so what is of interest to us is we want to find at what value of theta does sigma achieve its maximum value, right? Maximum, minimum values of very much interest to us, because all our designs for stress or strain are dependent on something reaching its maximum value, because when it reaches its maximum value, that's the point, or that's the thing what will fail. So in this case, we're interested in finding sigma max, that is, find the theta at which we achieve a particular, the maximum sigma. So these are known as principal stresses. So we need to find or compute theta for which sigma achieves maximum, and as a consequence, there will be a minimum sometimes. Okay, so in order to do that, we can use calculus, or you can also plot that as a function of theta. But the easier way is to use calculus. So what we do is we do d sigma d theta equal to 0, right? And then solve for theta. And that theta corresponds to the angle at which sigma will achieve its maximum or minimum value. If you want to check if it's maximum or minimum, you take the second derivative. If the second derivative is greater than 0, it's a minimum. If it's less than 0, it's a maximum. That's from calculus. So what we get is, in this case, we have 10 to theta. And I'll put P for the principal. It's called the principal direction of stress. 10 to theta equals 2 tau xy divided by sigma x minus sigma y. Okay, so the solution gives me this. So I'm skipping that derivation, but there is a derivation on how to get this. You won't be asked derivations in the exam. So once we get the principal, it's called the principal direction of principal stresses. Again, it'll be clear in a bit. So we can put this value back in this equation. Let's call this 1. Let's use a different notation. 1 and 2. So we can sub the value of theta in equation capital 1 and capital 2 and solve for sigma and tau, where you get the principal, where you put the value for theta p. So let's call this 3. Okay, again, I won't do the derivation. I'll just write down what you get as the final answer. So we'll sub in 3 in 1 and write a formula for sigma. We'll sub in 3 in 2, write the formula for tau. Yeah. Sure.
So you're saying the derivative of sigma, right? So equation above, you took the derivative of sigma and got tan to.
Yes.
Okay.
So I did A, then B. This was the answer. So substitute. I'm going to bring 2 T's there. Three in 1 gives sigma. So when you put that in, you'll see that you get 2 values for sigma. One of them is the principal stress, one of them is the maximum principal stress, one is the minimum stress. So I'll write Z1. Okay, so let me call that 1, and let me just put 2. Getting what is going to. Let me just put, you know what, let me put that sigma A and B. That's better. We'll confuse with something else which we come later on. So let's say that the principal stresses are sigma A and sigma B, and those will be sigma X plus sigma Y. Divided by 2. And then there's a plus or minus. The plus goes for A and B, the minus for B. Okay, so that's sigma A and sigma B, the principal stresses. And then what we can do is we can substituting 3, that is the expression for tangent 2 theta, into, that is the expression for tau, gives tau equals 0. So it turns out that the shear stress is 0 when sigma achieves a maximum value. So they both hold simultaneously. When sigma is that, sigma A, sigma B is the maximum value, tau is invariably 0. Okay. The second thing of interest here is, just like we found the maximum value for sigma, we need to find when does tau achieve its maximum value, because sometimes things will fail in normal stress, sigma, but they could also fail in shear. So we need to find the maximum shear stress. So the second thing is, just like this, compute theta for which sigma achieves maximum or minimum. We'll find compute theta for which tau achieves maximum or minimum. Okay, those steps are very similar. What you do is you first take the derivative of tau with respect to theta. That's step 1. The second step is solve for theta. And then once you solve for theta, you will get tangent to theta s, where now s denotes the direction of maximum shear stress, equals minus sigma x minus sigma y divided by. Okay, so just like we computed the maximum normal stress and maximum shear stress in the previous section for that particular theta, that is theta p, we can do the same thing here. We will substitute, let's call this 4. So we substitute 4 in here in 1 and in 2, and then find what the value for tau and sigma is. So let's call it tau A and B. They would be 2 stresses, shear stresses for that direction, sigma x minus sigma y divided by 2 square plus tau xy square. Okay, and then we'll also have for tau A, there's a normal stress. For tau B, there's a normal stress. It just turns out that that stress is the same, no matter what you put, tau A or tau B. So that normal stress in this case is sigma x plus sigma y divided by 2. Okay, so now we come to the Mohr circle. So how is this related to Mohr circle? So Mohr circle is just an observation made on the equations. So let's look at 1 and 2 again. I'm going to just rewrite 1 and 2 slightly differently. Okay, so let me rewrite 1 by moving sigma x plus sigma y divided by 2 on the left side. Okay, and then I'll keep tau as it is. Let's do that. So motivation behind Mohr's circle. So we write 1 and 2. So I'll write 1 as sigma minus sigma x plus sigma y divided by 2 equals sigma x minus sigma y divided by 2 cosine theta plus tau xy sine 2 theta. And then I keep the tau equation as it is. Minus sigma x minus sigma y divided by 2 sine of 2 theta plus tau xy. Okay, now it turns out that if you square these two equations and add them up, the 2 theta will disappear from the equations. Okay, so you can try this out if you want. So what you get is square both sides and add up okay, so you get sigma x minus sigma y square plus tau xy square. Okay, so the key motivation here is that this is basically the equation of a circle with center at, so the circle is along, it's not along xy, it's along sigma tau plane. Sigma is along the x-axis, tau is along the y-axis, and the radius of that circle is the thing on the right with the square root sign. So square root of sigma x minus sigma y divided by 2 square plus tau square xy. And the center of the circle is sigma x plus sigma y divided by 2 for the x-axis and 0 for the y-axis. So in other words, if you draw a circle like so, with sigma along the x-axis, tau along the y-axis. Then the center of the circle is sigma x plus sigma y divided by 2, 0. Okay, which you can see is over here. And then the radius of the circle is nothing but the square root of the thing on the right side. This looks like gamma r. And then once you make this observation, you can then go back and take that plane stress element which I drew, and then you can represent sigma x, sigma y on this plot. And then you can pretty much represent sigma, the sigma and tau for any angle. So the whole idea behind using the circle is that it just simplifies our life in terms of interpreting the stress, sigma and tau, for any orientation. It's so easy to read off the maximum stress. The maximum stress is this, right? This is the maximum stress. This is the minimum stress. Just by observation, if you know the center and the radius, you pretty much know sigma A, sigma B. We also know the maximum shear stress. So that's, I think I call that tau A. And then I call this tau B. Okay, so what I'll do is I'll show you how to now do this whole thing without, well, before we do a problem, let me just, now that we built the intuition, I'm going to show you how we can take that plane stress element, which I showed you, and then how do you plug that, take that, draw the circle from that element. Okay, so you can draw the complete circle without having to do, well, you need the equations though, but it's very easy in terms of how you can find the maximum stress and minimum stress without using any equations. So let's do that. And then we'll solve problems based on that. So draw a real big circle. Okay, that's close. This should pass through the center of the circle. It's a bit skew. Won't pick this up. That's good. Good enough. Okay, so we're looking at the plane stress element. So let's draw stresses on it. Sigma x, sigma y, sigma x, sigma y, and then tau's. Okay, so in a problem, you'll be given the plane stresses, those that plane element, the stresses, and you have to now construct the Mohr circle. By that, I mean you need to identify what the radius is, the center is, what the principal stresses are, and so on. So the way you proceed is as follows. First of all, we want to understand that every point on the Mohr circle corresponds to one orientation of that plane stress. So if I turn that by 5 degrees, it will be a different point. So by different point, I mean it's going to give me a sigma, which is on the x-axis. It's going to give me a tau, which is on the y-axis. And then there is a corresponding orientation. Sigma. So the key thing is each point on the Mohr's circle corresponds to an orientation of the stress element. Okay, so let's go ahead and figure out the maximum, minimum, and so on based on this. So what you do is, this is the procedure to follow when you're trying to draw the Mohr circle. First of all, you will be given the values for sigma x, sigma y, tau xy. Okay, draw the points sigma x, tau. So take this combination and then draw it on the Mohr circle. You can do that because the x-axis is sigma, y-axis is tau. So let's say that this point is somewhere here, somewhere randomly here. Right? Since you'll be given the numeric values, you'll be able to put it there. Then similarly, this corresponds to sigma x, right? Similarly, you can draw the coordinates of sigma y, tau xy. So this is sigma y, tau xy. Okay, so once you have that, you need to join these points. So this point all the way with the other point. And then wherever it passes through which, the x-axis, that is the center of the circle. And so the coordinates of the center is sigma x plus sigma y divided by 2. That's the x-axis, and 0 for the y-axis. Right? So all you need to do is dot those points, and then you have the center. Now, once you have the center, and once you have one of these points, the radius is as simple as measuring this distance, right? This is the radius. Yeah, I'm out of time. So the radius is basically going to be, you know, the numeric value for the center because sigma x, sigma y is given to you. You know, a numeric value for sigma x, tau xy because the numeric value is given to you. You just find the Euclidean distance between them and then you have the radius. Draw the Mohr circle from that. So the way this goes is as follows. First of all, this only one kind of rule you need to remember, that is sigma's positive is tension and negative is compression. That's the sign convention. And for tau, clockwise, okay, now normally clockwise is taken to be positive, but for Mohr circle, we'll take clockwise as negative. So that will be negative, clockwise, positive, counterclockwise. So what does that mean? I'll come to that in just a second. So now let's look at the Mohr circle. So this is the plane element, and in a problem in the exam or for your homework, you'll be just given this stress element, and you're told to find the principal stresses. For that, you need to draw the Mohr circle, right? So how do we draw the Mohr circle from that figure? This is how you proceed. This stress is shown as tensile stress. So it has a positive sign. Okay. Let's say this face is A, okay, and then this face is B. And you can do the same thing if you want with the face down and the left side. It's up to you, but really we need two faces to start thinking and drawing of the Mohr circle. Now on face one, we have on face A, sorry, we have sigma x as the tensile stress. It's positive, and then tau xy. If you see the direction of tau xy, it's counterclockwise. Yeah, my bad. So this should be actually opposite of this. Counterclockwise is negative. My bad. This should be positive. So clockwise we normally take as negative, right? For moments, you're just going to take it positive here, and then the opposite for counterclockwise. My bad on that. So you can see that this tau xy is counterclockwise. So we'll assume a negative sign. So the coordinates of the point A are sigma x and negative tau xy, just because it's counterclockwise. And hence, what I do is I draw a point here. Okay, now the circle won't exist. I'll just draw this point. I'll take a sigma tau axis, so assume a certain grid spacing, draw this point on that grid, right, which is going to be a coordinate. Then I'll do the same thing for B. On B, we have sigma y, which is upwards, and it is tensile, so it's positive. And then you can see tau xy on face P is clockwise. Clockwise is positive. So then I'll draw this point here, some value on the sigma y, and then the corresponding value for tau xy. And then I join the two lines from, this is A, this is B. The point where they intersect the sigma axis is the center of the circle. And you can verify that it's actually the arithmetic mean of sigma x, sigma y. That's why I have sigma x plus sigma y divided by 2. Okay. And then the radius of the circle is easy to find also, because if you know 2 points, one the center and the other on the circumference, then it's basically the Euclidean distance, which is you take the coordinates of the center, subtract from the coordinate of A, and then take the sum of squares. Right? You could also find it from the diameter. This line, the blue line, is actually a diameter. So you know the diameter, you can find the radius. Okay, so yeah, question. Yeah, so the convention is positive for clockwise, and you can see this. It has a tendency, well, this one is going to rotate this plane element in the clockwise direction if it was a force. So tau xy, you can find a sliding force, and that force rotates the plane element clockwise direction. That's all. Okay, so if all that explanation was confusing, I'll do an example where I'll do this all over again slowly. Okay, so that way it'll be easy for you to follow. So once I have those two things, then I can go ahead and find the things like principal stresses, sigma A, sigma B, maximum normal stresses, just by looking at the figure. Turns out that the maximum stress is, well, is when sigma attains the maximum value, so it'll be sigma A comma 0. That's the farthest most point on the sigma axis. That's going to be the maximum principal stress. The minimum stress is going to be here. Okay, just by observation, you don't need to know anything about those formulas. It will be sigma, the minimum value for stress is sigma B, that's all. And then for maximum shear stress, remember the shear stress is the y-axis. The maximum shear stress will be this point. And the minimum value would be here. So the coordinates of that point would be 0 for the x. Sorry, it's not 0, my bad. What's the x coordinate for that point? The center of the circle, right? So sigma x plus sigma y divided by 2, and then tau max. And that you can see just by, again, visualization. You don't need to do any math. Same for this point. So you found the principal stresses. Now, what about the principal stress direction? What does it mean to have a principal stress direction? So those stresses, maximum stresses, are for a certain incline, right? We want to find what that inclination is. And that inclination is actually, again, very obvious from this graph once you know how to think about it. So this is, as I said, and this is a note here, that each point on the Mohr circle corresponds to orientation of the stress element. So this point, for example, was the face A, when the plane stress element was as I've shown it. The point B is that point. Okay, that's at 90. So anything which is 90 degrees over here always shows up as 180 degrees on the Mohr circle. Okay, that's like the fundamental thing which you want to remember. So now if you want to find the angle of the principal stress, you always want to find the angle of the principal stress with respect to either face A or face B, right? Because if you want to rotate or find the inclination, we'll always find the inclination with respect to A or respect to B. So if you want to find the maximum stress, sigma A, with respect to face A, all you need to do is compute this angle. Okay, this is the angle made by face A with the direction of maximum principal stress. So there was this formula I wrote down, which came from calculus. That formula came from calculus, but you can find that 2 theta just by using that angle I just showed on that graph. This angle turns out to be 2 theta s. So all this is saying is, if you want to find that inclination on or show it on the plane stress element, then you need to turn that plane stress element by an angle theta in the counterclockwise direction. So going from here to here, you're going in the counterclockwise direction by an angle 2 theta. So you need to turn this face by an angle of theta, so something like this. That direction is the direction of principal stress sigma A. Okay, and then if you want to find the angle in which there's a maximum shear stress, then it's basically this angle. Goes from here all the way to there. And that was also a derivation. So again, the same interpretation, which is if you want to find that angle, should be theta s or theta p. Then you just rotate the element by angle theta s. So there are two things going on. One is that the convention is, this part of the convention is important. And then the second thing is that anything which is 2 theta on the Mohr circle is theta on the plane stress element. Okay, so that was sort of the theory. Now let's solve an example where I'll do this same construction slowly, but with numbers, and hopefully that would make it more clear on how to go about doing this whole process. Okay, so the stresses on the element are, there's a compressive stress on the face which is along the normal to the x-axis. There's a tensile stress on the other face, so let's call the sigma y, and that is 50 MPa. And this stress is sigma x, and that's 80 MPa. 80 MPa. And then there's a shear stress, which I'll show with a slightly different type of arrow. And this shear stress is 25 MPa, and this one is also 25 MPa. So by the law of complementary stresses, that stress has to be 25 on the top left, should be the same value in the bottom right. Can't have a different value. Yeah.
Are we given the directions of tau and sigma?
Yes. Yes, you will be given those things. Okay, so for stress element like this, the questions are: one, draw the Mohr circle. Second, compute the principal stresses and their directions. And then third is compute the maximum and minimum shear stresses and their directions. Okay, so let's review the sign convention because we'll be using it. So I said for normal stress, positive is tension, negative is compression. And then tau, it is positive is clockwise and negative is counterclockwise. So by this convention, let's call this face A, this face B. So by that convention, on A, we have a compressive stress on face A. So we would have a negative 80 MPa for the normal stress. For the shear stress, now you can see that the shear stress on face A, there's an arrow going downwards. Okay, and if you think about how will this element rotate about this point, the central point, it's actually going to rotate in the clockwise direction. Clockwise direction is positive, and so tau xy will stick the positive sign. Okay, 25 MPa. Okay, now let's do it for B. Sigma y is the stress at B. You can see that the stress is dead side. So the stress is going to be 50 MPa with a positive sign. And then if you look at the shear stress on face B, the arrow, you can see it's pointing from right to left. And that would turn the plane stress element in the counterclockwise direction. So the sign convention says it's negative. So negative 25 MPa. So I highly recommend that you do this step because this step will help us start drawing the two coordinates A and B. That will help us draw the Mohr circle. So I'm going to take those points, minus 80, comma 25, and then plus 50, comma minus 25, and draw them on a grid paper. Okay, if you don't have a grid paper, you can just make lines and just see that it's approximately looks all right, because then you'll have to get a circle to pass through it. Okay, so let's choose an origin, and then let's assume that each of these are 20 units plus so many. So if each of them are 20 units, then if this is the origin, then I need to find minus 80 on the x-axis. So 20, 40, 60, 80. So minus 80. And then since this point is 20, this is 40, 25 would be, that would be 30. So it'll be somewhere here. That's going to be 25. So let's see, A is minus 80 plus 25. So this is 25. Okay, I'm going to try to get the circle to pass through this point. And then the other stress is 50 on the x-axis and the minus 25 on the y-axis. So 20, 40, 50 is about here. And then 25 is this much. Okay, so I need to drive a circle through those 2 points. Okay, that looks okay. Okay, now I can draw the axis. This is my x sigma. sigma and tau. Okay, next step is to, well, let me put the coordinates here. This is A, right? Minus 80, comma 25. We can write it down, which exactly is copied from here. Minus 80 for the x-axis, 25 for the y-axis. Similarly, 50, comma minus 25 for B. Okay, now I just join the points A and B using a straight line, and that straight line should pass through the center of the circle. Something like this. You know, if it was drawn perfectly, then that point you can actually read it off the grid, but here it's actually just okay. It looks like it is at, it's around 10, but it's actually at 15 because it should be the arithmetic mean of minus 80 and 50, right? Minus 80 plus 50 is 30, minus 30 divided by 2, which is 15. So this point is minus 15, comma 0. So center is 80 minus 50. So I'm adding the two coordinates of points A and B. And then I can do the same thing for the y coordinates. 25 minus 25, that's 0. Sorry, I swapped it. Minus 80, thanks, plus 50. And then this should be 0 because 25 plus 25 minus 25, that's 0. That's 15, comma 0. Okay, now we need to find the radius of the circle. And that is, as I said, is you can get it from the Euclidean distance. So you can find the distance between A and B, which will give you the diameter, and then you half it, or find the distance between the center, let's call that C, and point B. So we can just use the distance between C and B. So the radius is the square root of the difference in the coordinates, x coordinates between C and B. So that's minus 15 minus 50 square plus 0, which is the y coordinate of C, minus 25, which is the y coordinate of B square. Okay, so if you do the math, it comes out to be 69.64. Yeah. Same answer. Okay, my goal is to do this problem this way and then show you how you can get it without drawing any more circle. So then you can compare the two. So those are the two key things you need. One is the center, and the second is the radius. So once you are done with this, you can then start solving for the other things, which are kind of easy based on this. So if you want to find the maximum stress, normal stress, let's call sigma A as the maximum stress. It's simply this. Sigma, here. This is simply the maximum stress, sigma A, comma 0. Right? And then the minimum stress is something is here, sigma B, comma 0. Okay, it's easy to see that it's simply the center of the circle plus or minus the radius. So if you add the radius, you get sigma A. If you subtract the radius from the center coordinate, then you get B. So sigma A is okay, let's call this X or sigma bar. So the sigma bar plus R, which would be minus 15 plus 69.64, and then sigma B, sigma bar minus R, minus 15 minus 69.64. $54. I think this is 69.6, but this is 6. This comes out to be 54.4. Right. No, 6. Sorry. Yeah, and so I've also shown it on the plot. Now, we also need to find the direction of the maximum principal stress, sigma A and sigma B. And then you can either go from B and find the angle with sigma A mixed with B, or you can find the angle sigma B mixed with A or B. It doesn't really matter. You can use either of them. You get the same answer. So let's find that just by looking at the figure, not using any equations. So the angle I'm looking for is this angle. And that angle is the principal stress direction. So it's theta, it's theta. It's 2 theta p. So let's see how to find that. Yeah, questions? Yeah, so anything on the Mohr circle is twice that on the plane stress. And you can see it easily by looking at angle between A and B is 90 degrees, right, from this figure, because A and B are at right angles to each other. If you look at point A and B, they're 180 degrees. And so everything maps to 2 theta. Okay, so I'm just going to use the trick to find that angle 2 theta p. I'm just going to draw that triangle over here just because it's cluttered on the figure. This is point A, this is point C, and this is 2 theta p. Okay, I need to find this, the width of the triangle, and you can see that it's basically, it'll be 80 minus 80 plus 15, but we're only interested in the magnitude, so it's going to be, I think, 65. Okay, and then we're interested in the height. You can see that simply 25. So tan 2 theta p is the opposite side, which is 25, divided by 65. And that is 0.3864. Then you can use inverse trig to find 2 theta p. That comes out to be 21 degrees. And so theta p is 10.5 degrees. Okay, and so this method actually doesn't really give you the sign. It's sort of not there in that calculation, but you can see from the figure, the Mohr circle, that sigma b is, if you want to go from A to sigma b, you need to sweep counterclockwise. So I'll just put this here, CCW. C Mohr circle. Now, the question has not asked you, but we can also draw the stresses corresponding to sigma A and sigma B, the principal stresses, on the plane stress element. So the planes, what we need to do in order to do that is we would need to rotate the plane stress element by an angle equal to theta p now, not 2 theta, because remember, anything which is twice on the Mohr circle is theta on the plane stress. And we need to do that 10.5 degrees counterclockwise. So what I'll do is I'll show you how that plane stress element looks when you rotate it by 10.5 degrees. So originally we had this was our original plane stress element, which was along the XY axis. Now I need to rotate by theta p counterclockwise, and that I should do that to the face A. So take face A, which is this face, rotate by 10.5 degrees, and you can rotate about the center. So it will look something like this. Where this angle is 10.5 degrees counterclockwise. Okay, but we're not done yet. We need to also show the stresses on this plane stress element. Okay, so we again go to the Mohr circle. Remember that every point on the circumference of that circle corresponds to an angle for the plane stress element. So in this case, when you go from A to B, which we have done here, face A would now have a stress of sigma B. So this is face A now, because it's turned by 10.5 degrees. Its stress would be sigma B, which is minus, I think it's 84.6. Okay. And then we know that this point here is going to be at 90 degrees to this direction. So it's always going to be on the other face. So that stress is going to be 54.6. So sigma A, 54.6, same over there. And then we see that the shear stress is 0, right? So there's no shear stress. You wouldn't show shear stress there because it's that direction of principal stress. Okay, so note that when we did this whole thing, we never ever used that formula which I wrote down. We simply used a grid paper, drew the points, drew the circle, identified the center, radius, and so on. Okay, now let's complete this. Part 3 asks us to find the maximum shear stress and its direction. So for the maximum shear stress, you can see that the maximum shear stress is going to be right above the center, this one, and right here. So this is tau max. And it's simply the radius of the circle, which we've already found. It's R, which is 69.6. And this point is tau min, which is minus 69.6. Just let me write that down on next page. Tau max min equals plus or minus R, which is plus or minus 69.6. Okay, that was the easy part. Now we need to also find the direction of the maximum shear stress. So for that, we do the same thing, which is either start from point A or B and find the angle from the point A to the maximum shear stress or minimum shear stress. So just choose this one. So we need to go clockwise by an angle 2 theta s in order to be at the maximum shear stress. Okay, so I'm going to try to find that angle by using trig. In order to prevent clutter, I'm just going to redraw that, only that corresponding, well, I'll draw this triangle actually here. Once I draw this, I'll be able to find 2 theta s, and then I will be able to draw the plane stress element when it is rotated. Let's just do, yeah. Theta p is the direction of which the principal stress makes with the face A or B. Is the angle with the maximum shear stress makes with either face A or B. So in this case, there are actually 2 angles there. I just showed you one. One of them is theta p. That's the angle made by face A with the minimum. In this case, it's the minimum stress. But then there's another angle which is, you go from here all the way here, and that's 2 theta p1, theta p2, but it just adds a lot of clutter. It's easier to find theta, the acute angle, than find the obtuse angle. If you want to find the obtuse angle, which is that angle between plane A and sigma A, then you just add, in this case, 180 degrees, and you should get it. Right? Is it 180 degrees? Yeah, 180 degrees. Yeah, just do one and then it's easy. Don't do both. It's just too hard. Okay, so let's draw this triangle and then identify the angles, and then hence identify theta s. So we see that the height is 25. And then this length is going to be, well, it's the distance from 80 to the center. So minus 80, minus or minus 15. So it's 65 units. We're only interested in the magnitude. And then this is 2 theta. Okay, so the formula is tan 2 theta s equals the opposite side, which is 65, divided by the adjacent side, which is 25. This comes out to be 2.6. If you do the inverse, tan inverse, then you get 2 theta s equals, get 69 degrees. So we want to find theta s. That's half of 69, which is 34.5 degrees. Okay. Okay, now again, the problem with using a trig is that we have not really identified, it doesn't really give you the sign of theta s. So for that, you just go to the figure and see how the max is with respect to A. You need to go clockwise in order to, you need to go clockwise from A all the way to reach tau max, right? So I'll just put that clockwise here, because that will be useful when I draw the plane stress element in the rotated configuration. Yeah.
So in this case, are we taking clockwise and positive or negative?
In this case, we are not really doing anything with the signs.
Okay.
We are just trying to use this CW counterclockwise to make a judgment on how we're going to rotate the plane stress element. Okay, yeah, but I'll show you how to use the signs later on. I'll just solve this problem using the formulas, in which case we can just use the actual sign. Okay, so let's draw the original element. And then we need to turn this element by 34.5 degrees in the clockwise direction. So this is face A. This is 34.5 degrees. Okay, and now what's left is to draw the stresses. That's the easy part. Now the stresses is something we need to go back to the Mohr circle to figure out. So in order to draw the stress, let's go to the Mohr circle. So we're interested in the, so we have already rotated the element, so we are over here. And so at this point, we have a normal stress of -15, which is saying that the stress on the each of the faces will be, well, it'll be -15 for the, this is face A, this is face A in the rotated position. So on face A, it will be -15. Okay, on the other face, which is the minimum, where the stress is minimum, the stress is also -15. That's the normal stress. So again, if you want to find that angle, it's just a clutter here, but you will go from here, dotted line, to here. Because the normal stress is -15. For this point, the stress is -15, 69.6. That -15 shows up. This one will also have -15. Okay, one last thing and we're done. We need to also draw the shear stress. Okay, the shear stress, as you can see, is on this face, the shear stress is 69.6 with a positive sign. And so now you need to work that convention backwards. So remember this convention where positive is clockwise, negative is counterclockwise. So if you see anything on the Mohr circle with a shear stress of positive value, it means it's clockwise. So let's use that here. So this is positive 69.6, which means it's positive, which means it's clockwise. So I need to show a stress of clockwise on face A. Face A clockwise. So that's the new face A, clockwise 69.6. And then you can use the same logic for the other part, which is this point here. It's going to be 69.6 with a negative sign, which is counterclockwise. So on the other face, it's going to have this direction, counterclockwise. CCW.
So are they always opposite?
Yes, that's complementary shear. And then you can just show that in the equal and opposite direction. This is a complementary shear. You'll always see that they are in the direction shown. They'll always be equal magnitude, and they will always be, one will be clockwise, one will be counterclockwise.